Hi there. So we're now out in the garage at the CNC machine, and I'm just going to show you how this is all set up with the interface electronics and the fourth axis itself. You know how some of those videos show you workshops that you really wish that you had that was the one you wanted? Well, this isn't one of those videos, so I'm not going to make any wide panning shots to show you the garage. So what I'm showing you now is the black box that has the embedded computer inside it. And so it's just a simple box. You can see the connectors there for the power and the serial port connection, which is actually connected to the USB of the Mach 3 computer system. The board is then sitting inside this. I've decided to connect the computer and this computer to the IBM PC and to the Gecko drives using flat ribbon cable that actually look like the parallel port connectors that are already there. So one of these, the long one here, is actually going over to the computer. This one is connected to the Gecko 540. Now the way I've connected these, one is a male and the other is a female connector. And so as a result, this is like an extension cord that you can put in between the computer and the existing parallel port cable. If you wanted to, though, you could connect this as the only cable that goes between the computer and the Gecko drive or the breakout board, however you've got your machine configured. Or even easier is if you wanted to, you can configure the computer here to be directly between a breakout board and an individual driver for the rotation axis, the A or B rotation axis. And that's even easier, and it's just a matter of setting up the wires the way you want to do it. We're using it with the parallel port wires. All I've done inside the box is to split out some of the individual conductors, 4 of them, that you need, and those 4 are diverted to the board and then from the board off to the output to the Gecko. And so those 4 wires again are the ground, a monitor for the e-stop, the step, and then the direction pulses for the A axis. So it's actually a really simple way of setting it up. This system then is going to be up by the main computer that's driving Mach, out of sight, out of mind. As soon as the machine powers up, this powers up as well, and you're good to go. So the whole objective is that this machine, this computer, is transparent from both the point of view of Mach 3 and the Gecko, which is receiving the pulses sequences. Neither one of them really has to know what you're up to with this embedded computer. So that covers the embedded computer that I've built to drive this system. This is just to show you in a little more detail the way that the fourth axis itself is set up. It's a NEMA 23 motor that's coming through. It's bolted to this panel, and then I've got a 4-to-1 reduction drive here to turning a pulley with an XL belt system, timing belt. The shaft is a 5/8 steel shaft that runs through to the working end where we attach the work. I've got some bearings that I bought at a local farm supply store. These ones have an unfortunate mount method to connect the shaft to the inner race of the bearings. It's an eccentric cam system, which really isn't ideal for this, but it does work. But I think it would be better to have perpendicular screws to attach the two together. It does work though. One of the ways that I've built this box that may be interesting is that rather than just bolting the flanges to the inside surface, there's a recess that's been pocketed into the wood that is very tight tolerance to the size of the flange. I think I've got a 1/2 millimeter extra space, which means that as built, the system is pre-aligned. It's just bolting it together to make it work. There's really no uncertainty on all of this. Grease fittings to keep it lubed up. The electrical connection coming from the Gecko 540 is here to a terminal strip at the bottom, and then the individual wires come up to the motor, and so you can really measure things and make sure that everything's working the way you want. I was a little concerned about how to mount the motor onto the system. Sometimes you see these done with a sliding connection so that you can tension the belt that way. I didn't like the way of doing that because in order to get this shaft to protrude far enough, I had to pocket into the thickness of this plywood, and it's about halfway through, which doesn't leave a lot of meat, especially if then you're cutting grooves for the bolts and a longer slot for the NEMA 23 panel mount. So I decided instead to have the motor fixed on the system, so it's securely bolted to the panel, and I've got this sliding idler pulley which can be adjusted from inside and out to apply the correct tension on the system. And that actually makes it a very tight system. I'm very happy with the way that works. The turning radius here may be a little small for this belt, for the back bending radius. It's about 1 inch for this particular bearing. I think it should be a little bit larger, but frankly these belts cost $3, and if it wears out a little bit prematurely, I'm not going to worry about $3 too quickly. These flanges are mounted onto the plywood walls using T-nuts that are embedded into the wall, which means that I can bring the pulley very close to this outside surface without having to worry about nuts or interferences, and it's a very nice fit that way. The whole box can be then closed up with hard panel like this, and that seals it in, tries to keep it as dust free as possible. One of the things that I've found though is that the motor, when spinning at high speed, actually gets quite warm, and so I'm a little worried about this building up heat. I think part of the problem is that you're running a stepper motor in a continuous mode, which is unusual, but also because it's firmly attached to the wooden wall here, there's really no heat sinking available to the motor. And so I may have to change that by either replacing this whole thing with an aluminum panel, adding a ventilation fan, or something along those lines. We'll see. I've run it for several hours and it works well, but I just wondered whether this is in the long term viable. You can see a slight step out here. I needed to do this to get the belt on and off because this is a very tight tolerance. This is, I believe, a 4-inch diameter gear, and there's only 2.5 inches between the center of my rotation axis and the tabletop itself. So I had to dig that in a little bit into the plywood base, but that's all it took. So it's a very simple design. Looking at the tailstock now, actually we can come around here. The tailstock is also a pretty simple device. This is set up with a 5/8 threaded rod acting as the main axis of the system, and it's held in place at this point and at this point by nuts that are embedded in the plywood piece. And so it's a bit of a trick to get it really tight, but once you get it set up, it's very, very secure, and there's actually no sideways wobble on this. Unlike a normal nut, which is used here, I chose to use what's called nylocks for both ends here and at the other end here. The nylock, when you first buy it, has this nylon washer embedded into one end of it, and when you first use it with the 5/8 rod, you actually cut the groove into the nylon, and that makes it a very, very tight fit. In fact, it's so tight that to turn this shaft from within these boxes, I have to put a wrench on the end. It's a little bit more tighter than I expected it to be, but it seems to work very well, and there's absolutely no play on this shaft at all. It's a very, very secure system, so there's nothing that I can do to move that. The shaft continues through to the end. I've got this nut that's embedded into this shaft that allows me to easily adjust the height or the length of this thing, and when I turn that back, it locks and jams against the coupling collar here to make a very, very tight fit, and this is not moving at all. It's very, very secure. Now, one of the things that you have to think about for making the 4th axis work is how you're going to actually hold on to the wood. On the working end of it, this is the shaft that's protruding from the motor end, the headstock, and the way I've got this set up now is I'm using this piece as my prong to bite into the wood. And so the way this is built, it's just a coupling nut with some nails welded to it, so it's quite a savage looking piece of metal, with a center brass bolt that I put a slight taper on. And so all you do is you mark the center of the work that you want to use as the rotation axis, you put the brass point onto that, and then you back off the brass until the points of the nails are touching the wood. Then you press it in just with your hand, and when you then back out the brass all the way, you can hit the back of this with a hammer to drive the nails into the wood, and that's extremely secure. It's not going to move anywhere. And because when you take it all the way home, the end of the coupler is flat to the wood, it means you've got a good perpendicular axis as well. This brass piece could be used also then on the tailstock, because this is all 5/8 hardware. So you could screw this in and give a tapered piece here, which would be a dead tailstock. A lot of people do something like that. I've got a slightly different approach. My coupling nut here is going to be the seat for a ball bearing. And this ball bearing is remarkably smooth. When you feel that motion, there's no give at all. There's no evidence of any play on it whatsoever. And so the idea is that at the end of the tail end of the wood, I'm going to drill a small hole that will take the ball bearing, and then that gets pressed up into that, and then the turning wood will slide on that ball bearing. And so it's halfway between a live and a dead tailstock, so this is my zombie tailstock. The other nice thing about using the ball is that it makes it very insensitive to misalignment angles. You've got a large amount of angle there that you can turn it on, and this turns just as freely with no evidence of play whatsoever. So it's a really nice rotation axis with very solid connection up, down, sideways. So I'm pretty pleased about the way that looks. Okay, so that's enough of that. The next step is to install the black box with the Mach 3 computer, and we'll see how this thing spins.